All right, people, welcome back. The next topic on the list is one of my favorites for this semester. It's a theorem called Green's theorem. So let's see what's going on with this one. First, we need a little bit more jargon. So last time we met what is a closed curve, and we saw before that if C is a closed curve and big F is a conservative vector field, then the integral along C of big F must equal to 0. Okay, but what if big F is not conservative? Then is there any other clever way to integrate it along a closed curve? Well, the answer is kind of, yes. So we're going to tackle this question just today for vector fields on the plane. That's what Green's theorem is really about. So before we do that, though, we'll need a little bit more terminology. First, not just closed curve, but what's called simple closed curve. And so a simple closed curve is a curve in the plane that can be parameterized by a function r of t, which is x of t in the first component and y of t in the second component, where the two parameters, the endpoint parameters for t are a and b. And the simple closed part is that this curve is going to be subject to the following two conditions. The first one is that the endpoints are equal, so that r of a equals r of b. So that's just saying C is a closed curve. Again, we met that notion last time. So the simple part comes in with the next stipulation, that whenever you have two parameters, t1 and t2, that live between a and b but aren't equal to each other, then r of t1 does not equal to r of t2. So in other words, this curve has the same endpoints, but everywhere in between, it never crosses itself another time. That's the idea. So there's no other self-intersections. And, oh yeah, another stipulation here too, or another sort of implication after this, this property is that the parameterization R only traverses then once around the curve. So there's no repeating other than just at the endpoints. So good. So here's an example of a simple closed curve. Let's say if that's going just once around there, that would be a simple closed curve. This is an example of a curve that is a closed curve because it looks like it could start and end at the same point, but it is not simple since it crosses itself at this point there in the middle. Okay? Notice that if you were a not simple closed curve of this form, you could maybe like envision this as just being broken into two simple closed curves, yes, that happen to just kind of butt up against one another. So that might be one kind of fix around the fact that that one is not simple. But if that is the kind of fix that we're working on here, then we really only need to consider these sort of fundamental pieces, these little simple closed curves. So they'll be kind of the situation where we're looking today. All right. So let's suppose that we have one of these simple closed curves parameterized by the function little r of t. And let's say that D is the region of the plane that is enclosed by this curve. So here's our example of a simple closed curve. Inside here is the region D, right? A simple closed curve in the plane kind of has an inside and an outside. So let's let D denote the inside. And so imagine yourself now walking along that simple closed curve by starting at R of A and ending at R of B. And if on your walk, when you're walking along the edge of this region D here, if that region is always on your left, that inside of the curve is always on your left, then we say that little r gives a positive orientation to the curve C. So on this one here, I have drawn the sort of arrow here indicating that if we parameterized and going around this direction around this curve, if we were walking on that little curve along that way, that the inside D here would always be on our left. And so this arrow indicates that this curve has been given a positive orientation here. That if we had a parameterization walking around this way, this would be what we call positive orientation. I know it's kind of awkward. It's kind of a new idea, and there's a lot more that we can say about it. But I think that this is enough to get us by today, to just think about orientation. So, okay, so we've noted that here. Okay, great. So, Green's theorem then says, let C be a positively oriented, simple closed curve in the xy plane, and let D be the two-dimensional region of the plane that is enclosed by that curve C. And now let big F be a vector field. So we have P of xy in the first component and Q of xy in the second component. These are both scalar valued functions now. And suppose, too, that those functions P and Q have continuous partial derivatives. Then the line integral of F over C is equal to the standard double integral over this two-dimensional region D of the function now, which is given by the difference of the partial derivative of Q with respect to X minus the partial derivative of P with respect to Y. Now, we're not going to actually prove this theorem today. We are just going to use it in a couple of different clever ways. But note that we have seen something like this before. We have seen these two culprits here come about when we were discussing conservative vector fields, right? We discovered that if a vector field was conservative, then this difference would have to be 0, I believe. And if this difference wasn't 0, then the vector field in question would be not conservative. So in particular, if we have a vector field that's not conservative, i.e. this difference is then not 0, then we have some kind of clever, novel way to do a line integral along a positively oriented simple closed curve by instead trading it for a double integral, which at this point in your life may be slightly more familiar. In fact, at this point, you might be kind of a whiz at double integrals, and you might prefer double integrals of just ordinary functions over nice regions of the plane to these kind of more exotic things, line integrals of vector fields. I don't know. But let's see. So, right, so that's just putting that in prose down here and saying that Green's theorem will allow us to trade the line integral of f along c for the ordinary double integral of this scalar valued function over this region D. That's very nice. Okay, and so before we get to any examples, I just want to talk about a couple of different notations that you might see floating out there with regard to things about Green's theorem. So you might see this funny looking integral that has a circle kind of in the middle of the integral sign. And all that really indicates to us is that the parametrization of the parametrization given to us by little r gives a positive orientation for the curve C. So I think that kind of stands for, sort of like oriented curve. So we're integrating f along an oriented curve. Okay, so if you see that out there in the literature, that is all that's being discussed. Now, there could be different conventions about what gives a positive orientation, so you might need to watch out for that if you're sort of operating in a different textbook or in a different course. But that is what this notation is meant to be given, that there is a particular orientation, a positive orientation, either one way around, say clockwise or counterclockwise. Okay. And so also recall from previous section, the first section of this chapter, 16.1, that we can write line integrals a little bit more explicitly by saying if f is given by the function p in the first component and q in the second component, then we can write this line integral of f along c as the line integral along c of the expression p of xy dx plus q of xy dy, or for short, just p dx plus q dy as the integrand. That's kind of nice. So then another way you might see Green's theorem being stated is that if you have this oriented integral along c of the expression p dx plus q dy, that it may be traded for the ordinary double integral over d of the function, the partial derivative of q with respect to x minus the partial derivative of p with respect to y. This is a rather nice looking statement. So join us in the next part of this talk where we'll do some fun examples of Green's theorem, which are some of my favorite examples from this entire course. So be sure not to miss those ones.